going to present my paper, which talks about some Paley-type graphs on the commutative ring Zn. This is joint work with my supervisor, Professor Anwita Bhowmik On. So let's begin. Okay. So first, I shall give a brief outline of my talk. Firstly, I will give an introduction about what Paley graphs are, how they are connected to Ramsey theory, and how they are linked. Then I will move on to the graph that we have defined, which we call the Paley-type graph. We denote it by Gn. We shall study some of its basic properties. Next, I will talk about Gn for some particular values of n, and we shall see that certain character sums come into play. And finally, I will talk about our main results and some related lemmas which were used to prove the results. And lastly, I will present my references. Okay. So the introduction is like this. So we all know what the Paley graph is. So named after Raymond Paley. So Raymond Paley in 1933, he published a paper on Hadamard matrices, which actually inspired people to define the Paley graph. So the Paley graph was defined as a graph independently by Sachs in 1962 and by Erdős and Lenny in 1963. So as we know what a Paley graph is, so consider Q as a prime power such that Q is congruent to 1 mod 4. Then let FQ be the finite field with Q elements. So the Paley graph of order Q is the graph which has vertex set as FQ, and two vertices A and B are connected by an edge if the difference is a non-zero square in FQ. Okay, so Paley graphs form a really nice family of conference graphs, and they are connected, self-complementary, and strongly regular with these parameters, as Shamil said. Paley graphs have been studied by graph theorists and number theorists alike. But here I would like to state one particular motivation to study Paley graphs, which is related to Ramsey theory. So for that, let Gn denote a graph with n vertices and Gn bar be its complement. Then let Km of G be the number of complete subgraphs of order m in a graph G. Then we have this Km of n, which is this expression. So here the minimum ranges over all graphs on n vertices. So now what is the Ramsey number? So the diagonal Ramsey number R of n, it is the smallest positive integer such that I take any graph with Rm or more number of vertices, then it should contain a complete subgraph of size m. And if it doesn't, then its complement should contain a complete subgraph of size m. So the smallest such positive integer is called the Ramsey number Rm. So here we note that Rm is the smallest n such that Tm of n is positive. So from here we see that there is some link between the diagonal Ramsey number and this Tm of n. And in turn, Tm of n depends on this expression Km of G bar. Okay. So seeing this link, this Tm of n was studied. So in 1962, Erdős gave this upper bound on Tm of n, and he gave this conjecture of this limiting value of Tm of n. Okay. Although this conjecture was not entirely true, but it turned out that for prime, so if I take n to be a prime, then this was true. And for again primes, T3 of P and T4 of P were studied by Goodman and Thomason. Okay. So here we see that Km of G plus Km of G bar, for this expression, Paley graphs are minimal in certain ways. So since Paley graphs are self-complementary, it is enough to just study Km of G. Okay. And we note that the Ramsey number R4 is 18. So to show that R4 is not 17, I have to come up with a graph with 17 vertices such that neither the graph or its complement has any complete subgraph of order 4. So the Paley graph on 17 vertices is the answer to that. So that is why this is how the Paley graphs have come into the picture to study this TM of n and in turn to study Ramsey numbers. So now the focus shifts to the study of K4 of G, where G is a Paley graph. So in 1981, Evans, Pullum and Sheehan, they gave a simple closed formula to calculate K4 of GP, where P is a prime and GP is the Paley graph with P vertices, where P is congruent to 1 mod 4. Okay. And this work was extended by Atanasoff et al. In 2014. So instead of a prime, they took a power of a prime. So Q is a power of a prime congruent to 1 mod 4. And they took the specific case where P is also congruent to 1 mod 4. Next, so now that the Paley graphs were studied, so after that, Paley graphs also started getting generalized. So I will list some generalizations here. The first is that by Anwita and Cassetta. So they define what we call the cubic and quadruple Paley graphs. So the cubic quadruple both have the vertex set as FQ. So for the cubic graph, Q is congruent to 1 mod 3. And two vertices A and B are connected by an edge if the difference is a non-zero cube. For Paley, it was square, here it's a cube. And similarly for quadruple, it has to be a fourth power. So the difference has to be a non-zero fourth power. And here the condition has to be Q congruent to 1 mod 8 so that -1 is a fourth power in order that the graph is well defined. Okay. After that, in 2006, Lim and Prager, they further generalized. So Anwita and Cassetta generalized only for cubes and fourth powers. So Lim and Prager took this to be some general k. So if I take any k greater than or equal to 2, an integer, now if I take any prime power q such that q is congruent to 1 mod k if q is even, or q is congruent to 1 mod 2k if q is odd. So why do I take this condition? Nothing but to make the graph well defined. So then the generalized Paley graph GK of Q is the graph with vertex set FQ, where AB is an edge of the difference A minus B is a non-zero kth power. And for this generalized Paley graph in 2021, Dorsey and McCarthy, they gave a formula to compute the number of complete subgraphs of orders 3 and 4. Okay, so computing for order 3 was comparatively easier, and in some cases they gave a simple closed formula. And for computing subgraphs of order 4, they gave the results in terms of finite field hypergeometric functions. And they also showed that the zero values of K4 of GKQ and K3 of GKQ, they give lower bounds for certain multicolor diagonal Ramsey numbers. Okay. The next generalization is given by Nicholas Veitch in 2006. So he considered FP where P is a prime, and he fixed some T in FP. Then he defined 3 graphs. Two were defined as undirected graphs, and the third was a directed graph. Okay, so the vertex set in all 3 cases is FP. So in GT of P, XY is an edge if both x minus ty and y minus tx are quadratic residues. And in GT prime of P, either of the two has to be a quadratic residue. And for the directed graph HT of P, so x to y is an edge if both x and x minus ty are quadratic residues. Okay, now that we are done with the introduction, I will move on to our graph, Paley-type graph, which we call as GM. We will study some of its basic properties. So the Paley graphs or its generalizations have been studied on the finite field FQ. So instead of a prime power q, what if we consider just a natural number n and consider that as the vertex set? So taking a natural number n, one thing that can come to one's mind is Zn, so which is a commutative ring. Okay, so that is how the idea of defining a Paley-type graph on Zn has come about. Now to define the graph, for the Paley graph, for an edge to be well defined, Q had to be congruent to 1 mod 4. So for our graph also, we need such a condition. So for the Paley graph, the vertex set was FQ. Here we consider the vertex set as Zn. And the edge set for Paley graph depended on elements of FQ star, powers, squares in FQ star. Here, instead of just omitting 0, we consider the set of units. So we consider Zn star, which is the set of units in Zn. Okay. So now that this part is done, we try to see that when an edge is well defined. So we see that -1 is a square if and only if n takes the form n equal to 2 to the power s, p1 to the power alpha 1 up to pk to the power alpha k, where pi's are primes congruent to 1 mod 4 and s is either 0 or 1. And we exclude the cases n equal to 1 or 2 because in these cases the graphs are trivial. Okay. So after getting that condition, we define the Paley-type graph on Z. So this is the formal definition. So the vertex set is Zn and AB is an edge. So AB are elements of Zn. So if the difference is congruent to some square modulo n, then we have the edge AB. So first we had found out the values of n. So that led to this proposition, as I just said. Okay, next we look at some properties of this graph. The first is that we know what a regular graph is. It is one in which every vertex has the same degree. So like the Paley graph was regular, we also see that Gn is regular. And for n, Gn has degree equal to phi n by 2 to the power k, where phi is the Euler-Toshin function. Next, we know that a graph is self-complementary if it is isomorphic to its complement. But the Paley graph was self-complementary, however, Gn is not. So here we are losing out on a very important property. So unless n is a prime, Gn is not self-complementary. Okay. The next is that Gn is not a complete graph. If Gn would have been a complete graph, then there would not have been much to talk about this graph. So we find that Gn is not complete. But Gn is connected. So this is not very difficult to see. So if I take any two vertices x and y, suppose x is less than y in Zn, then x plus 1, x plus 2 up to y. So this forms a path because 1 is always a square modulo n. So Gn becomes connected. Now, by this fact that 1 is also always a square modulo n, we see that Gn will always contain a spanning cycle. But we see when is the graph exactly a cycle. So Gn is a cycle if and only if n is either 5 or 10. Next, a graph is called vertex transitive. If I take any two vertices in the graph, I will find some graph isomorphism sending one vertex to the another. So here we see that Gn is vertex transitive. We note that Paley graphs were also vertex transitive. Okay, next we go to, we take some particular values of n and we find Gn, and we will also go through some character sums. Okay, now for Paley graphs, to compute the number of complete subgraphs of a particular order, we saw that certain character sums were in the picture where the quadratic character was used. So here also, to do the same, we try to define an appropriate quadratic Dirichlet character. Okay, so first we define what is a Dirichlet character. So if I fix some n, either an integer or a natural number, then a function psi from z to the complex number c is called a Dirichlet character modulo n, if it has the following properties. So psi of 1 is 1. Psi is completely multiplicative. If A is converted to B mod n, then psi A equals psi B. And if A is not relatively co-prime to n, then psi of A is 0. And so epsilon is usually called the trivial character modulo n, which is defined like this. So it takes 1 only if x is relatively prime to n, otherwise it takes 0. And it turns out that the set of Dirichlet characters mod n forms a group. So for that, corresponding to a character psi, we define psi bar as another character. So psi bar of A is nothing but the complex conjugate of psi of A. So taking psi bar as the inverse of psi, we see that the set of characters form a group and the identity element is epsilon. So we also have psi times psi bar equal to epsilon, as I said. And if psi is not equal to epsilon, then over x ranging in Zn, psi of x is 0. The sum of psi of x is 0. Okay, now we are looking for a character psi such that it will give 1 if and only if x is a square modulo n. Similarly, how in Paley graphs we had that the quadratic character took 1 only if and only if the element was a non-zero square. Now to find such a character, we define 3 possible candidates. The first is the Jacobi symbol, which we know is a Dirichlet character. The second possibly is a character. So for suitable n, when a to the power phi n by 2, here again phi is the Euler-Toschen function. When a to the power phi n by 2 is convenient to plus or minus 1 modulo n, we may define chi2 of a as a to the power phi n by 2 modulo n. So why we are doing this is because for the Paley graphs, we saw that a to the power q minus 1 by 2 is either plus or minus 1. So similarly here, we are doing the same. So we will check later whether this kind of definition indeed forms a character or not. And the third definition is chi3 of a, which takes 1 if a is congruent to a square modulo n and takes minus 1 otherwise. So it turns out that the Jacobi symbol chi1 does not satisfy the condition 1. Okay, so we cannot take the Jacobi symbol at all. The next proposition says that if Zn star is not cyclic, then chi2 becomes the trivial character. Okay. So if we take Zn star not to be cyclic, then we cannot use chi2 as well. And the next proposition says that if Zn star is not cyclic, then there will exist some A and B in Zn star such that A, B, and AB are all non-squares. And from this, it follows that chi3 also cannot be a character unless Zn star is cyclic, because then chi3 of A times chi3 of B should have been minus 1 times minus 1, which should be 1. But we also get for that AB that chi3 of AB is also minus 1. So chi3 cannot be a character unless Zn star is cyclic. So from these 3 propositions, we see that if we take Zn star to be cyclic, then we can use chi3. And it turns out, in that case, chi2 equals chi3. Okay. So by a famous result of Gauss, we know that Zn star is cyclic if and only if n is either 2, 4, p to the power alpha where p is an odd prime, or 2 times p to the power alpha where p is an odd prime. Okay, so these are the 4 cases where Zn star is cyclic. And among those cases, we omit the cases where n is even because there cannot exist any complete subgraphs of order more than 2. So since our aim is to calculate the number of complete subgraphs of orders 3 or 4 or higher, so that's why we omit the cases where n is even. Okay. Now, now that we know that we have to take n such that Zn star is cyclic, so we need to take n equals p to the power alpha where p is an odd prime. Now for that case, we have a result. And before stating that result, let me introduce some notation. So let G be a graph, G equals PE. So if GI is a family of edge disjoint subgraphs such that the edge set of G can be written as a union of the edge sets of GI. So basically, the edge sets of GI form a partition of the edge set of G. So in that case, we write G is the direct sum of GI. Okay? And if GI is isomorphic to H for every I in the index set, then we write G equals the direct sum of H. With this notation, we have this result for the case n equals p to the power alpha, where p is a naught prime, p converted to 104, and alpha is a natural number. So this is our result. So it turns out that, since Zn star is cyclic here, we can take a unique quadratic character, let us call that chi. Okay, then if G of P is the Paley graph of order P, we see that a copy of the Paley graph exists in the graph Gn. In fact, not just one, P to the power alpha minus 1 copies of GP exist in Gn. So what we are doing is we are taking P to the power alpha minus 1 copies of GP. So they have their edges amongst themselves, and apart from that, there also exist edges between the copies. So that is how we are partitioning the edges. Okay, so suppose we are taking one copy of the Paley graph GP. We take one vertex in that copy, and we see that what other vertices in other copies are adjacent to this vertex. Okay. So this k of 1 comma p minus 1 by 2 is a star. It is complete Paley-type graph. So that is how we have partitioned the edges. Okay. Now we come to the main part where I talk about our main results and some related lemmas. So before stating the main results, let me start with the lemmas. So from here on, since our focus is on the case where Zn star is cyclic, so we take n equal to p to the power alpha, where p is converted to 104. So in this lemma, we do not meet the condition p converted to 104, but this lemma leads to the next one, where the condition p to the power 104 is needed, and we see that if chi is the quadratic character, it is the unique quadratic character of order 2 and quadratics order 2. So then chi will have period p. And this next lemma says, so it computes some sum over chi, and inside is a quadratic, inside is a 2-order polynomial and degree 2. So A and B are constants in Zn. So depending on A and B, we have 4 different cases. Okay, now that we are done with the lemmas, we go to our main results. The first is this I've already said. So okay, so we have called the quadratic character to be chi, and since 4 also divides the order of Zn star, so we take a character of order 4 and we call it psi. Now we already know that Gn was vertex transitive, and it turns out that if we take this subgraph H, which is induced by the set of squares in Zn star, then H also becomes vertex transitive. So why did we take this H is because in order to calculate the number of subgraphs, complete subgraphs of a particular order, if we want to use the property that the graph is vertex transitive, then we can reduce the calculation and calculate the number of complete subgraphs of a lesser order. Okay, so it will turn out that the lesser order will lead us to H. This is our first result, which computes the number of triangles in Gn. So this is given by a simple closed formula depending on P and alpha. So the proof of this uses the vertex transitivity of the graphs Gn and H. So since the graph is vertex transitive, each vertex will contain the same number of triangles. Number of triangles containing any vertex. So take 0. So a triangle containing 0 means the remaining two vertices should be squares in Z and star. And the difference should also be a square in Z and star. So that is nothing but the number of edges in H. Because I took H to be the subgraph induced by squares in Z and star. And again, since H is vertex transitive, we can further reduce to the number of edges in H containing 1. Because 1 is a vertex in H. So thus we are led to this simple character sum depending on chi, which was the quadratic character. Before stating the next theorem, we list some lemmas. The first is again this sum on chi. So chi of x square minus a, where x ranges in Z and star. So this is given by this value. The next is if I want to calculate the cardinality of this set. So x in Zn, where n is p to the power alpha, such that x belongs to Zn star. So p does not divide x is equivalent to saying that x is in Zn star if n is p to the power alpha. So so x is in Zn star and 1 minus x square is also in Zn star, such that chi of 1 minus x square is 1. So 1 minus x square is again a square in Zn star. So the cardinality is given by this value. The next lemma says that, so there are two sums, double character sums. The first is capital X. So this sum has index x and y ranging over Zn, and S0 is a sum which has lesser number of terms. So here the coordinate pairs x, y are in capital X. So capital X is what? All those coordinate pairs in Zn cross Zn such that x, y, 1 minus x square, 1 minus y square, and x square minus y square are all in Zn star. Then we have a relation between S0 and S. And this is nothing but expanding the sum S and breaking it into smaller parts. The next lemma, which is the main lemma to state for the main theorem, this says that, so again chi is the unique quadratic character, and psi is a character of order 4, and n is of course p to the power alpha, where p is common to 1 mod 4, and let j of psi and chi be the Jacobi sum of the characters psi and chi. Then this capital K, which is this double sum, where x and y are ranging in Z and star, this can be written in terms of the Jacobi sum. So square of the Jacobi plus the square of the complex conjugate. And to prove this, what we do is, so this, the method of the proof has been inspired from the paper of Ivanis, Kulam and Shihan. So since chi has order 2 and x and y in the sum, they are elements of Z and star. So I can divide the term by chi of x square times chi of y square. Okay, after doing that, I see that k can be written in this form. Okay, after writing in this form, what I want to do is, I want to replace x and y by two other variables, suppose u and v. So x minus 1 by y and y minus 1 by x, these I want to take as my new variables. But for that, I need to ensure that the substitution is at all possible or not. Okay. So to do that, what we do is, we exclude the case where p divides x plus y minus 1. Okay. So if p divides x plus y minus 1, we see that the sum is minus 2 times p to the power 2 alpha minus 2. Okay, so then k is reduced to this. And now here, so this bigger sum in the last line, this one. So this side, if I call it as capital U, and I want to write capital U as capital V by introducing two new variables. So, so that is possible because I have excluded the case where p divides x plus y minus 1. Okay. So after doing that, we get that capital K becomes of this form. So in this, the last line, the outer sum depends only on the variable t, but this inner sum, it also depends on u. It depends on both u and t. So to evaluate this inner sum now, we refer to this theorem 2.7 of this paper by Berndt. So what they've done is, they have done in the case of a finite field. So we use the same idea, which, so since chi is the quadratic character and psi is a character of order 4, so psi square is a character of order 2, but there is only one character of order 2, which is chi. So I can say psi square is equal to chi. And so replacing chi by psi square, I have this. So here I see that, so I want to, this u square term is here. Okay. So to remove this u square term, if I just want u, I need this term 1 plus chi of u. Because anyway, u is in Zn star. So 1 plus chi of u is non-zero only if u is a square. Otherwise, it is 0. So using that idea, we have that the inner sum boils down to two terms, and each of the terms depend on the Jacobi sum. So the first term is this psi bar of t times j of psi and chi, and this is the second term. Okay, now you just compiling this information, we have that k is j of j square plus j bar square. And this ends the proof of the lemma. So we can go to the main result now, which is to compute the number of complete subgraphs of order 4. Okay. So this is the result. So if p is congruent to 1 mod 4, alpha is a positive integer greater than or equal to 1, and n is p to the power alpha. Chi is the unique quadratic character mod n, and psi is a character of order 4. J of psi and chi is the Jacobi sum. Then k4 of Gn, which is the number of complete subgraphs of order 4, is given by this formula, which depends on p, alpha, and the Jacobi sum. Okay. So to prove this, again we use the vertex transitivity of the graphs Gn and H. So here we are reduced to finding the number of triangles in H containing 1. Now let f of p to the power alpha be the number of triangles in H containing 1. So we have to evaluate this f of p to the power alpha. Okay. Now to do that, we take this set capital X. Okay. So this is a subset of Zn cross Zn such that x and y, x, y, 1 minus x square, 1 minus y square, and x square minus y square are all elements of Zn star. Okay. Then f of p to the power alpha is 1 by 8 times this cardinality. This is because if I take any coordinate pair x, y, then plus minus x plus minus y will also give me the same result. Also, if I just reverse, so if I take it, instead of xy, if I take the pair yx, that will also give me the same result, the same triangle. Okay. So that's why f of p to the power alpha, to compute that, we need to divide by 8. Okay, so 2 times 2 times 2. Okay. So now we are dividing this set X, we are partitioning this set into 8 parts, depending on the values chi of 1 minus x square, chi of y minus y square, and chi of x square minus y square. Okay. So each value is either 1 or minus 1 because the elements are in Zn star. So if beta I is the cardinality of AI, then we see that beta 1 is 8 times f of p to the power alpha. Okay, so that means we have to find beta 1. So individually, rather than finding beta 1 individually, what turns out is that we find some relations between the beta i's. Okay, so we see how. So for example, if we consider A1 union A2, then here you see that chi of x square minus y square can be either 1 or minus 1. So the only restriction is on chi of 1 minus x square and chi of 1 minus y square. Okay. So using a previous lemma on cardinality, we find that the set has cardinality this value, which we denote as capital A. Similarly, the cardinality of A3 union A4, we call it capital B, which is this cardinality. Again, we find that A1 union A3 and A1 union A2, they have the same cardinality because we find a bijection between them. So since A1 union A3 has cardinality beta 1 plus beta 3, and so for A1 union A2 beta 1 plus beta 2, we find that they are equal. Okay. So in this way, we find other relations also among the beta. Okay. Namely, we have this 7 relations. Okay. So A and B are fixed values depending on P and alpha. Now, we have S and S naught, which we also encountered in the previous lemma. So S naught, in S naught, since the indices depend on capital X, so the coordinate pairs X, Y are in capital X, and capital X is the union of A1 up to A8. So I can break the sum in terms of the beta i's. And using the relations among the beta i's, I find that ultimately S naught is depending on f of p to the power alpha. Okay, so finding f of p to the power alpha means finding S naught. And since S naught is again linked to S, so ultimately I have to find S. Okay. So now to find S, what we do is this. So we remove the terms where either P divides X or P divides Y. Okay. Because in those cases, the terms become trivial. So removing those cases, we are led to this. And again, this removing this x's, since we want to remove this x square y, we want to remove the squared things. So we add these terms 1 plus chi x times 1 plus chi y. Now we break this sum into 3 parts: I, j, and k. Now I and k, these are comparatively easy to evaluate, and you find that they are equal. So they are 2 times p to the power 2 alpha minus 2. So we are left to calculate capital K, but if you notice, capital K is nothing but the last lemma which we had discussed, which I had said was essential, most essential, which was in terms of the Jacobi sums. Okay, so just replacing those values, we get S is depending on P alpha and the Jacobi sum. And now just tracing back, we find f of p to the power alpha in terms of capital S, and hence the number of complete subgraphs of order 4. This completes the total of our work. And these are my references. So here, Anwita and Cassetta, so here the cubic and quadruple Paley graphs were talked about. In this paper, the notation of direct sum was used. This was the computation of complete subgraphs of orders 3 and 4 in the generalized Paley graph, which was defined by Lim and Taylor here. And this is the paper on which they computed the number of complete subgraphs for prime. This is Paley's original paper of 1933. I'm done. Thank you.
Okay, Anwita, thank you very much for your talk. Are there any questions to the speaker?
Do you know the automorphism groups of these graphs, GN?
No, I have not studied the automorphism groups.
Oh, that would be quite interesting to know them.
Yes, yes. I have not. I have produced some, maybe one or two automorphisms, but I do not have any idea about the whole group.
Okay, thanks.
Any other questions?
So I have a question.
Yeah, sure, Kyle, please. Yeah, sure.
So do you know if there is any work on like estimating the number of complete subgraph with higher order, like for example, a size 5 or larger?
Thing is, currently no, because by the same logic, if I go by vortex transitivity, then I will come back 2 steps to computing triangles. For order 5, then I need to compute triangles, but then the character sums will become more complicated and they will involve 3 variables. For example, for 2 variables, if the character sums, there are 2 summations depending on 2 variables, then I could have used hypergeometric functions. But for 3 sums, I do not know if it can be reduced to a more nicer form.
Okay. And do you know why people are interested in counting the number of complete subgraph with order 3 or 4?
That is, I think, because it started from the Paley graphs. So as I said that, Ramsey number, then that expression Tm of n to be this Tm of n, this minimum over all this line. So here, if you notice km of g bar. So here k means the number of complete subgraphs of order m. So since to find out Ramsey R of 4, we needed to find out k4 of g. So maybe because of that, the interest went to calculating k4 of g or maybe k4 of other graphs as well. Since the graphs have a nice structure, which is you can use vortex transitivity, and again the subgraph H that I said, that is also vortex transitive. So you could again come down a step and calculate edges. So maybe that might be a possible reason.
Okay, thank you very much.
Thank you.
Any other questions? Well, if not, then let us thank again Anwita for careful explanation of all her results obtained jointly with her supervisor and actually showing us the ways how to prove all these results. Thank you very much. Yeah.